So since the last class was a makeup lecture, there's one important point I want to make at the end of the lecture. I just want to make sure everyone is here now. So if you look at these two links I gave, you may want to check them after class. So I just want to talk about these two links very briefly. So when you have an optimization problem, you may wonder what type of software you can use to solve a given optimization problem. So this page is called the installation guide for a software named Jump. Jump is like the Pyomo in Julia programming language. Okay. So the developers of Jump did a pretty good job of summarizing all the solvers that are available. Okay. So for example, here you can see the first column is the name of the solver. You can check things like Baron and Groovy are here. And then the last column, it says it supports. It outlines what type of problem this particular solver can solve. Right? So if you have a problem you don't know which solver you can try, then you can refer to this page. Okay, I'll put the link in the slides. So the other question you may be wondering is that if I know those solvers, which are the good solvers I should try, right? So that comes to the other link. It is called the Mittelman benchmark. So Hans Mittelman is a professor at Arizona State University. Every year he benchmarked those solvers for different problem types. If you go down the list, for example, he has benchmarked linear programming solvers, right? And then also mixed integer programming solvers, semi-definite programming solvers. If you click on, for example, the link on the SDP solvers, yeah, maybe the font is too small here. So here's all the solvers he benchmarked that can solve SDP. Okay, those include solvers like COpt, Mosaic, and so forth. Yeah, and then the first row of those this benchmark result are across all the benchmark instances, what are the geometric mean of the runtime, right? So 1 is the best, right? So the first one is the best in this case. Okay, whenever you have a new class of problem, you may want to refer to this website. Actually, Mittelman update this result every year because every year the developers of the solver will update their codes, and then you have to benchmark again. Okay, so today we are going to start a new topic on Lagrangian dual and optimality conditions. It is related to linear programming. Remember, we covered Lagrangian dual for linear programming. So in this lecture, we are going to extend that to general nonlinear programming problems. And in linear programming, we also talk about optimality conditions. You may, if you recall, one of the optimality condition is like the reduced cost to be greater than or equal to 0. The other optimality condition in terms of primal dual is that you have a both primal and dual feasible solution, and then you have complementary slackness. Right? So we are going to extend this linear programming optimality condition to nonlinear programming in this lecture. Okay, so the problem we want to consider in this lecture is a generic nonlinear programming problem where you have fx can be nonlinear smooth functions, and then the hi and li are the inequality and equality constraints. So here we do not assume, yeah, can you close the door? Yeah, so we do not assume convexity. Most of the results in this lecture will still hold even if you have non-convex problem, right? Of course, we will pay special attention to convex problem because usually in convex problem you have things like strong duality. Okay. So first of all, we would like to talk a little bit about a very simple optimality condition. It is called a first order optimality condition in the literature. So let's assume you have a f, which is a convex optimization problem, and it is differentiable. And X denote the feasible region of this optimization problem. Recall that in this case, we do assume convexity, right? In the next few slides, we will remove the convexity result. So the first order optimality condition says a point X star is optimal if and only if X is in the feasible region. Of course, if you want to be optimal, at least you have to be in the feasible region. Then we have this condition here. The gradient at X star transpose Y minus X star has to be greater than or equal to 0 for all the Y in this set X. Okay, so a simple interpretation is written here. This condition implies we cannot find a feasible direction at X star that leads to a decrease in the value of Fx. Okay, so geometrically you can think about this way. Let's assume this set is a feasible region. It is convex. Let's pick a point X star here. Okay, and then this condition says if you have the gradient of F, for example, the gradient can be this direction. Let's suppose this is the gradient of F at X star. Then it says the angle between the gradient at X star and all the directions you can pick that keep X feasible is less than 90 degrees, right? This is basically says if the dot product of these two vectors is greater than 0, that means in this 2D plane, their angle is less than 90 degrees, right? For example, if you pick any point Y here, let's just pick an arbitrary Y, and then you take Y minus X. So this blue vector is Y minus X star here, right? And the angle of those two vectors are greater than or equal to 0, right? That's what it says. And you pick any Y, this angle is always less than 90 degrees. But one caveat here is that the first order condition is not so easy to check, right? In order to check whether you satisfy the first order optimality condition or not, you need to check for all the Y that is feasible, right? And there are infinite number of Ys you should check. Okay, this is more like a property to help you understand the problem rather than help you develop a new method. So let's give a very simple proof of this first order optimality condition. Before that, let's write the first order optimality condition in an algebraic form, right? So X being optimal means that X star being optimal means that for all the Y in the set X, Fx star has to be less than or equal to Fy, right? That's just say X star is an optimal solution within the set X. And the theorem says it is equivalent to taking the gradient at X star with Y minus X star. Then for all the Y, the dot product has to be greater than or equal to 0. So let's first prove the direction, which is, this is like a necessity condition, right? So let's suppose the right-hand side hold true with this gradient condition hold. Then because F is a convex function, then this is nothing but the first order characterization of a convex function, right? So this part of the equation is the first order. This equality is true because F is convex. If you have forgot, you can check. This is called the first order characterization of a convex function. Okay, then after you write down the definition, we are pretty much done. Since we already know this part is greater than or equal to 0, then this whole thing should be greater than or equal to Fx star. Right? That's a condition given to you. Then basically we show that Fx star is the optimal solution here. Okay. Now we show the other direction. Suppose X star is the optimal solution, but there exists a Y with the condition being violated, right? This is like proof by contradiction, right? We have been using this technique multiple times. So suppose you have a point Y that violates this condition. Then we consider a point ZT. ZT is a convex combination of Y and X star, okay? And the trick we have done before is that we just calculate the directional derivative with respect to t. Then it says if you take the directional derivative here, then it says the directional derivative is exactly equal to this part, which is by assumption you assume is strictly less than equal to 0. Then since the function is continuous, if you pick a sufficiently small t, then you are going to decrease the value of fx star, right? Therefore, that shows x star is not the optimal solution. Okay. Any questions here? Okay, so just summarize the idea real quick. We want to show that when x star is optimal, then this inequality always holds true, right? So the idea is we are going to prove by contradiction. We assume the other way is true. The other way is like there exists a y such that this condition is violated, meaning that this gradient times y minus x star is strictly less than 0. Then we can find some sort of contradiction using the condition. The way we construct the problem is that we take ZT to be a convex combination of y and x star. So as t goes to 0, ZT will go to x star, right? As you can see here, if you take the difference of f ZT and f x star and let t goes to 0, this is nothing but the directional derivative at x star. And by assumption, by our contradiction is strictly less than or equal to 0, then you can show that if you move along this line segment between y and x star, we are going to have something strictly less than x star. In other words, you have already identified a descent direction such that you can find a smaller value than fx star. Okay, so that's the proof of the first order optimality condition. Then we are going to switch gears and talk about Lagrangian dual for general nonlinear problems. Okay, so note that the result of Lagrangian we show here will not be restricted to the convex case. It also, most of the results here also holds for non-convex problems. Okay, so first of all, we define the Lagrangian function as follows. We have the original function fx. Then you have the Lagrangian multiplier. For example, here for each of the inequality constraint, you multiply them by a variable ui greater than equal to 0. Why you have to define ui greater than equal to 0? Because we need to derive a lower bound in the Lagrangian, right? So this is a less than equal to constraints. Then you multiply by ui greater than equal to 0. It's the same thing as we've done in linear programming. And for each of the equality constraint, let's just assume we will multiply them by Vj. Since it's an equality constraint, we do not need to restrict the sign of Vj. Okay, so then here's the Lagrangian we are talking about, where we define u to be greater than equal to 0, v belongs to real numbers. Okay. So an important property we have already shown in the linear programming case is for any x that is primal feasible, we always have this Lagrangian function being a lower bound of the original function. Why that is the case, this can be shown very easily. So here's the definition, nothing but the definition of the Lagrangian function, right? And if x is feasible, we have hi to be less than or equal to 0, and Lj equals to 0, right? So if Lj, each of the Lj inequality is 0, we already know that this whole thing is nothing but 0, right? And by definition, we also have all the ui to be greater than or equal to 0, right? So for each of these ui term, we are multiplying a greater than 0 term by a less than or equal to 0 term. So this whole part is, this whole part must be less than or equal to 0, right? And if you add them up, you are essentially adding fx with a less than or equal to 0 number, right? So that's why the Lagrangian function must be a lower bound of fx if x is a feasible solution, okay? Yeah. So now let's define something called the Lagrangian dual function, which is minimizing the x over, sorry. So this part, let's define a Lagrangian dual function here. Okay, so this GUV is called the Lagrangian dual function. If you remember in the linear programming class, we have already done something similar, right? You dualize some of the constraints, and then once you define this Lagrangian function, you take the minimum of x, minimum of the primal variable, and then define this as the dual function, okay? Now the idea is to show that this Lagrangian dual function is also a lower bound of the primal objective. So how we are going to show that? Let's do it step by step, okay? So first of all, let's realize that due to this result, this result we have already shown here, for any feasible x, this Lagrangian function is a lower bound of fx, right? For any feasible x. And of course, if this is true for any feasible x, it is also true for the optimal x, right? Because the optimal fx star is nothing but a feasible solution, okay? So that's why you can show the first part of this inequality, right? This part is true because x star is feasible, right? So for all feasible x star, you have this Lagrangian function being a lower bound, okay? And now we go to the second inequality here, where it says I'm minimizing over all the feasible x for a given uv. Why this is true here? Any thoughts? Why this part of the inequality is also true? Yes?
Because that's the minimum.
Yeah, exactly, right? So x star is the optimal solution to the primal problem, right? But here I'm saying I'm picking the minimum over this Lagrangian function. Of course, it's smaller than whatever x star is, right, by definition. Okay, so now what about this inequality? Remember the difference between this part and second part is that I'm throwing away the condition that x being feasible, right? So here's x has to be feasible in the feasible region. Here I'm letting x to be unrestricted, okay? So of course you are relaxing the problem, right? That now x is unrestricted, it will give you a smaller value than x being feasible, okay? So if you put all these together, what we have done is we show that for any u and v as a Lagrangian multiplier, the optimal primal solution is always lower bounded by this Lagrangian function. Okay. This is a very important result, and then it doesn't rely on the problem being convex. Actually, this is also true even if the problem is, let's say, mixed integer or mixed integer nonlinear, whatever function you can have, right? So if you try to check each of why each of these inequality is true, the argument we have used is only like x star being feasible, and then we are removing the feasibility condition and so forth. Okay. And let's call this function the Lagrangian dual function. Okay. And it gives you a lower bound. Now let's derive the Lagrangian dual function for some very simple examples, kind of to give you an idea how to derive the Lagrangian dual function. Okay, so of course, the problem that is slightly more complicated than linear programming problem is quadratic problem, right? We already derived the Lagrangian dual function for linear program, that is the linear programming duality. Now let's show it for the quadratic program, where you have a quadratic function x transpose qx plus c transpose x, and the constraints are nothing but the standard form of a linear program, right? So this is one level. If you remove this x transpose qx part, this is just linear program, right? And here we assume q is a positive definite, okay, just to make sure the problem is strictly convex. And you can write down the Lagrangian as this, right? So you just multiply, let's say we multiply this A transpose AX minus B equals to 0 constraint by V, and we multiply this part of the constraints by U, right? So now you get this Lagrangian here, which is minus U transpose X, V transpose AX minus B. You just basically throw the constraints to the objective. Now the Lagrangian dual function is saying we are minimizing over x for this Lagrangian here, right? So what is the minimum of this quadratic function? How do you derive that? So here's the result here. Yeah, so we just take the gradient, set the gradient to 0, right? Since it is a strongly convex function, we already talked about the optimality condition if the function is convex. So we just take the gradient over this function, basically partial L, partial x. That will be the first term is a quadratic term, that will be qx, and you take all those linear terms with respect to x. That will be plus c minus u minus a transpose v, right? And you set this to 0, okay? Now, because this Q matrix is a positive definite, then it has a closed form solution, right? We have n variables and n constraints, and this Q matrix is invertible, right? You just take the inverse of this matrix, then you get x equals to the inverse of Q times minus c plus u plus a transpose v, right? So that's the optimal x. And then you just replace the x with x star and plug it back into this equation. You basically get this result here. Okay. Is this part clear before we move to the next slide? Yeah.
I have a doubt in the last slide.
Yeah.
When x is not in the feasible region,
yeah.
Like why can't I have hix greater than 0, and then when I'm moving out of the feasible region, then min of just on x can be like greater than when X is feasible, right?
Yeah, so there is no guarantee that, so when you optimize this function here,
Yeah.
there is no guarantee X is feasible, but it is a lower bound.
Yeah, so when X is not feasible,
Yeah.
I might have H greater than 0. And
Yeah,
then
yeah,
it
yeah.
won't be a low bound then, right?
Yeah, so but it will still be a lower bound because of this argument. Because if X is you see, so when X is a feasible solution, it is a lower bound, right? But now from this term to this term, you are removing the feasibility constraints, right? Of course, this part is lower than X being feasible. So even X being feasible is already a lower bound. Now you are removing the feasibility condition. It can only get even lower, right? Although you may get H greater to 0, but you can be compensated somewhere else, maybe, right? That's a way to think about it. Other questions? So now let's talk about a slightly more complicated case. I want to use this to give you a very small review of linear algebra, because a lot of times I find maybe the reason people are not following optimization is because people are not fluent in linear algebra. So we will use this to give you a review of linear algebra. Okay, so what if the Q matrix is singular, right? In the previous slide, we assume Q is non-singular, right? Q is positive definite. But here, we remove the condition Q is non-singular, Q is positive semi-definite, right? So when you have a matrix which is singular, then the linear system may not have a unique solution, right? There are many cases that can occur. For example, if you take the derivative of this term, you may find out that there is no solution. Okay. So actually, the Lagrangian dual function will look like this when Q is singular. So here I'm replacing the inverse with a pseudo-inverse. Here. In the last lecture, we talked very briefly about pseudo-inverse. If you forgot about that, it's okay. We will review that later. And it says we are replacing Q by pseudo-inverse. And also, we need an extra condition, which is this linear coefficient should be in the row space of Q. Okay. So why that is the case, we will give you a review of linear algebra. Then we will derive this Lagrangian dual function. Okay. Yeah, so let's do a quick review of linear algebra. In your graduate level math class, did you cover this like row space, column space, and so forth? Okay, that's great. But we'll do a very quick review of the vector space for matrix A. So let's say if A is a m by n matrix, then the column space of A, denoted by COA, is the linear combination of all the columns of A, right? And you can write it as AX for X is any real number. It's basically you are using X as a real number to generate all the linear combination of the columns of A. And the dimension of the column space is equal to the rank of A. And row space is the linear combination of the row vectors of A. You can write it as A transpose F or A transpose Y for all the Y in dimension M. Okay, so if we are talking about a symmetric matrix, then the column space is equal to the row space, right? Just like in the previous slide, we are talking about Q is a symmetric matrix, then the row space and column space of Q are the same. And the null space of a matrix is a set of vectors such that AX equal to 0, right? So you can think about X as you take the linear combination of the columns of A and then make them to be 0. And the dimension of the null space equals to n minus the rank of A. Right? This is a well-known result in linear algebra. And there are some orthogonal properties. First of all, the row space and the null space of A are orthogonal. Right? Remember, if you this is the definition of the null space is nothing but each row of A multiply x is 0, right? So x must be orthogonal to each row of matrix A. Okay, and the column space and the left null space which is the null space of A transpose, they are also orthogonal. Okay, this is just by definition. Any questions for this slide? Hopefully you are still familiar with those results. Now let's consider this problem. We are minimizing an unconstrained quadratic function, 1 over 2x transpose qx b transpose x plus c. So let's consider when is this quadratic problem unbounded. This is a unconstrained quadratic problem, right? When it is unbounded. So there are a few cases where this problem will be unbounded. The first case is that if Q is not a positive semi-definite matrix, then this problem will be unbounded. Okay. Why that is the case? Because by definition, if Q is not PSD, then there exists an eigenvector with negative eigenvalue, right? Okay, that's just definition of a matrix not being PSD. So let's assume let X be alpha times this eigenvector, okay? And you plug in X into this equation, you will find out the rest of the problem is a quadratic function of alpha. You have an alpha squared term and an alpha term, right? So if remember this lambda is the eigenvalue of the matrix, and lambda is negative, right, by definition. Okay, so if you set alpha equals to infinity, this problem will be unbounded, right? So this is nothing but saying this function is a function of alpha where the curve is facing downwards, right? This is just a quadratic function with only one variable alpha. Okay. So that's one case. But now let's assume the matrix is PSD, but this vector B is not in the row space of Q. In other words, B cannot be expressed as a linear combination of the columns of Q. Okay. So if that is the case, we know that there exists X such that, oh, I should write it as, there's a typo here. I'm saying there should be a Y. So if B is not in the column space of Q, that is equivalent of saying there is a component of B that is in the null space of Q, right? So usually a vector can be decomposed by a vector in the row space and a vector in the null space. So if B is not entirely in the row space of matrix Q, it must have a component in the null space of Q, right? So that is saying that there must exist a vector Y such that Y is in the null space of Q and Y has a non-zero product with B. Without loss of generality, we just assume this product is strictly less than or equal to 0. Right? If it's greater than or equal to 0, just take minus Y, right? Then it will be less than 0. So now let's set the vector X equals to alpha Y. Then if you let alpha equals to infinity, it also gives you unboundedness. Why that is the case? Because if you plug in X equals to alpha Y, right? So the first term is X transpose QX. That will be alpha Y times Q alpha Y, right? Since we already know QY equals to 0, right? Y is in the null space of Q, then this part of the term is 0, right? And you are left with a linear term. Will be B transpose alpha times B transpose Y. Plus a constant C. Right, since we know B transpose Y is strictly less than 0, then if you set alpha equals to infinity, this problem will be unbounded, right? Okay. Are the first two bullet points clear? It's nothing but a review of linear algebra. Okay. Now we are left with the second bullet point, which is if Q is PSD, and also B is in the range space of Q, right? What will happen in this case? So in this case, since Q is PSD, we know the problem is convex, right? For a convex problem, the minimum is obtained at gradient equals to 0, right? You just take the gradient of this quadratic function. The gradient of this function is Qx plus B equals to 0, and find the solution of this linear system that will be the optimal solution. Okay, and this problem must have a solution because B is in the row space of Q, right? So if B is in the row space of Q, B is also in the column of space of Q because this is a symmetric matrix, and then this linear system has a solution if and only if B can be expressed as a linear combination of the columns of Q, right? Since B is in the row space of Q, this linear system must have a solution, right? Okay, are those three bullet points clear? Okay, if not clear, maybe you want to read your notes in your linear algebra class and then revisit that, okay? Yeah. So now we are left with this question, how do we solve these linear systems, right? So the next slide is also going to be a review on linear algebra, okay? So how do you get the solution of Qx equals to B when Q is a symmetric matrix, okay? Here we assume Q satisfy the conditions we give you. Q is positive semi-definite, and then B is in the range space of Q. So first of all, if Q is the full rank, then you can just take the inverse of Q multiply by B, right? If Q is, and then if Q is not full rank but B is in the row space of Q, then you can show that one of the solution is the pseudo inverse of Q multiply B. Okay, we are not going to show the proof here because I think I'm almost running out of time. And besides this solution, you can add a z vector where z can be any vector in the null space of Q, right? So if z is in the null space of Q, Q multiply z equals to 0, right? So you can always add this vector z here. Okay. And recall that how do you get the pseudo-inverse? The pseudo-inverse is nothing but if you take the eigenvalue decomposition of a symmetric matrix. Okay, so let's assume this eigenvalue decomposition is lambda I times qi transpose. Then the pseudo-inverse is you just take the reciprocal of each of the lambda. Okay, that's the definition of a pseudo-inverse. And there is a proof that you can show that this is indeed a pseudo-inverse. Okay. Maybe someone can ask a question. I see a few people look a bit confusing. Okay, so now to put it together, what we have discussed is the following, right? We are considering when this minimization problem is unbounded. We already talked about two cases this is unbounded, when Q is not positive semi-definite, when B is not in the row space of Q, the problem is unbounded. And then if we are not in the first two cases, i.e. Q is positive semi-definite and B is in the row space of Q, then you just take the gradient of this quadratic function and set the gradient to 0, right? And now how do you solve this system? That will be the next slide. There are two cases. When Q is a full rank, you take the inverse of Q multiply B. When Q is not full rank, you can think about this as just you take the pseudo-inverse multiplied by B. You can remove the Z if you wish. Okay, so here's a proof why the solution is looks like this. Okay. Yeah. Yeah. So let's go back to the previous case, and you can double check why this is a case, right? Why you got this Lagrangian dual function. Here, remember, when we are minimizing this Lagrangian here, we are essentially minimizing a quadratic function, right? So this is a quadratic function of x, right? So that's why we are minimizing this quadratic function. We are essentially, it's the same thing as minimizing this, right? We just change the notation to a generic notation. Then we discussed two cases where the problem can be unbounded. First is that Q is not PSD, but here we give Q is already PSD. We don't need to care about this. The only thing we need to care is whether this linear coefficients is in the row space of Q or not. If it's in the row space of Q, then you get something related to the pseudo-inverse of Q. Right? If it's not clear, you can go to the next few slides and then apply the results to this slide. It shouldn't be too hard to derive this result. Okay. Okay, so now let's consider a slightly more difficult problem, right? So the last problem is that we have quadratic objective, which is convex, then we have linear constraints. And now let's consider a slightly more complicated case where we have a quadratic objective function, and all the constraints are quadratic. Okay, all the constraints are x transpose qi plus qi transpose x, and so forth. So QCQP has many applications we are going to talk about in the latter half of this lecture. How do we solve generic non-convex QCQP problems? Right. So here I did not say the Qs has to be PSD, right? So if all the Qs are positive semi-definite, this is a convex problem, right? But here we do not assume the problems are convex. You just assume the Q can be any symmetric matrices, right? So this is a NP-hard problem to solve. But still, even for this non-convex problem, we can derive the Lagrangian dual for this convex problem. Okay. So how do we do that? We will multiply each of these constraints by lambda I and aggregate all the constraints in the objective, right? This is just standard way of taking the Lagrangian dual. And then the Lagrangian dual will look like this. It is a quadratic problem, right? So here, each of these matrix Q, the matrix Q lambda will be the original Q naught, which is in the objective function, plus lambda I, the summation of lambda and IQi, right? So we are aggregating the constraints by multiplying them using lambda I. Okay. And similarly, for the linear term, we have the original objective and some linear combinations of, actually it should be Cornick combination because lambda I has to be greater than 0. Okay. So you are aggregating those. All right. But even if you aggregate all those constraints in the objective, as you can see, this Lagrangian function is still a quadratic function in X, right? So it is a linear in lambda, but quadratic in X, right? Okay. So first of all, when you are trying to get the Lagrangian dual, we are minimizing over X, right? So for each of the lambda, we are minimizing in X. Here, lambda is fixed when you are deriving the Lagrangian dual function, right? Okay, so this is the Lagrangian dual function we are minimizing over X for this quadratic problem, right? How do we derive the Lagrangian dual? You can use the result from the last few slides, right? Essentially, we are discussing when this quadratic function is unbounded, and then when they are bounded, what will be the optimal solution to this quadratic problem? Okay, just to repeat the result, The idea is when Q lambda is not positive semi-definite, then you have G lambda is unbounded, right? And when Q lambda is positive semi-definite, but Q lambda, this linear coefficient, is not in the row space of Q lambda, then this Lagrangian function is also unbounded, right? That's the two cases we've talked before. And then if Q lambda is positive semi-definite, and then Q is in the row space of matrix Q, then remember that we are talking about something related to the pseudo-inverse of Q, right? When you are solving the linear system equations, it's related to the pseudo-inverse. If you don't feel comfortable with pseudo-inverse, you just assume this is something related to the inverse of Q, right? You just replace the inverse of Q with the pseudo-inverse, then life is good, okay? Any questions here? Okay. So all of it is related to just solving an unconstrained quadratic problem. When it is unbounded, then you got infinity. When it is not unbounded, then you derive the conditions and get the result. Okay. So next, I'm going to show a quite shocking result. When I first read about this, I feel this is a very shocking result. It basically shows that the Lagrangian dual of a QCQP is an SDP. So in the previous lecture, we covered something related to semi-definite programming problem, right? So essentially, you can show that this Lagrangian function G lambda is nothing but this semi-definite programming problem. So remember, in the dual, we are when we are solving the dual problem, we are maximizing over G lambda, right? Because the dual gives you a lower bound, you want to provide the tightest lower bound, right? Okay. So why it is we have this equivalence? So the way to show this is equivalent to the dual problem is by using the Scher's lemma we discussed in the previous lecture. Okay. So let's take a look at this matrix here. Okay. First of all, this constraint is saying that this big matrix is positive semi-definite, right? By using the Scher's lemma, the positive semi-definiteness of a big matrix is equivalent to the positive semi-definite of two smaller matrices, right? And if you use the Scher's lemma, the first thing we can show is that this PSD constraint is equivalent to two things. First, we need to have the Q lambda to be positive semi-definite. Then you can take the Scher complement. That would be, so if you don't remember it, you can check the Scher's lemma. The other thing we need to enforce is R lambda minus D minus 1/2. So you just multiply these two diagonal terms using the pseudo-inverse of Q lambda, right? And this is greater than or equal to 0. Also, Q lambda is in the row space of this matrix. Okay. Then amazing, right? After using the Scher's lemma, basically we recover something very similar to this condition. Okay. If you do the rearrangement of the term here, right? So here in the original term, we only have something related to Q and R, but this variable D is what we introduced to represent the objective, right? So if you manipulate a little bit about this inequality, we basically get the D has to be less than or equal to R lambda minus okay. And as you can see, the right-hand side is nothing but the objective of this g lambda function, right? And you enforce the d has to be less than or equal to the objective function, and since we are maximizing over d, right, then d will always be equal to this term here in the optimal solution. Right? And that's why you can show the Lagrangian dual of QCQP is an SDP. Right? And one interesting thing to note is that the original QCQP might be a non-convex problem. And now you take the Lagrangian dual. The Lagrangian dual is an SDP, which SDP is a convex problem. Right? It kind of tells you that for any non-convex problem, if you take the Lagrangian dual, you can get a convex problem, perhaps. Right? Actually, this is indeed the case. We will show in the next. Yeah. So this is a proof. Yeah. Any questions regarding the previous slide? Okay. So if it's clear, then let's show that the Lagrangian dual is always a convex problem. Okay. So first of all, let's consider the Lagrangian dual problem here. We already show the dual function is a lower bound of the primal problem, right? And hence, in order to get the best lower bound, we are going to maximize over this Lagrangian function. So this is a dual problem we are talking about. For QCQP, this problem is an SDP, as we just showed, right? And key property we have is weak duality. The dual optimal value is, let's assume, is G star. Then it is always a lower bound for the primal problem, right? Note that this lower bound always holds, right? Even if the primal problem is non-convex. Okay. We did not use anything related to convexity in this derivation. So now we are going to show that this dual problem is a convex problem. Why that is the case, we can just write down the dual problem here. As you can see, this is the Lagrangian here. And the Lagrangian dual function is derived by minimizing over x, right? Okay. And we talk about a property in the second lecture, which is if you take the pointwise maximization of some convex function, then the function is convex, right? So think about, let's say we take a bunch of, maybe this is the x-axis. We take a bunch of linear functions. Right? So if you take the maximum of these three linear functions, you get this function here, right? That's the maximum of these three linear functions. And as you can see, the shape is convex, right? So actually, this is a homework problem in the first homework, right? If you do a pointwise maximization over certain convex functions. So here, since the functions we are talking about is linear in U and V, right? So those functions are linear although they are nonlinear in X. So if you take the maximization over X, it's like you are maximizing over all the X for a bunch of linear functions, right? So for each fixed X, this function will be a linear function of U and V, right? You can think about you are getting the maximum over an infinite number of linear functions of U and V, right? So here I'm just plotting a finite number of linear functions, right? So this is nothing but you are taking the maximum over an infinite number of linear functions. And after you do that, the function will be convex in U and V, okay? So if this function is convex, then if you take the negative of that function, that is a concave function, right? And since we are maximizing over G, U, and V, then you are maximizing over a concave function. That's why the Lagrangian dual is always convex. Okay. Now the other property for generic nonlinear programming problem is strong duality. We already showed weak duality, right? But on the other hand, we have observed that for some of the problem, we do have a strong duality. We already showed the special case in linear program, right? If you have a linear program and then either the primal or the dual is feasible and bounded, then you have strong duality. We also show the same thing for conic program, right? If you have the primal which is feasible and bounded, then you have strong duality, and same thing for the dual. But this is a result for generic nonlinear programming problem. This is a so-called Slater's condition. Okay, so remember that in this case, we do require convexity when you are talking about strong duality, right? Intuitively, you can think about this is true because convex problems are polynomial to solve, right? And strong duality is quite a strong result because if the dual problem is always convex, it can be solved in polynomial time. Then you kind of show that the primal problem has to be polynomial solvable in order to have strong duality. That's a way of thinking about that in terms of computational complexity. So we see that the primal is a convex problem. In other words, the function f and h, the inequality constraints are all convex, and the equality constraints are all linear, right, in order for the problem to be convex. Then the Slater's condition says if there exists the strictly feasible x in Rn, strictly feasible means that all the constraints, all the inequality constraints are strictly satisfied. Then you have a strong duality. Okay, that's a condition people have used to prove strong duality, but we are not going to show how to prove that. You can just take it for granted here. All right, so another concept people use in optimization method is a so-called duality gap. Okay, so why do we need duality gap? The reason is that the dual problem always provides you a lower bound, right? So if the primal problem is not far, the primal solution is not far from the dual solution, then you know you are very close to the optimal, right? So the duality gap gives you a way to terminate your algorithm, right? Okay, so that's the main difference between a rigorous algorithm and a heuristic. Usually if you run a heuristic method, things like genetic algorithm or simulated annealing, this type of algorithm, there is no guarantee you are at a global optimum, right? But in this class, we are not going to talk about those heuristic, where all the algorithm we talk about will have certified global optimality. Okay, of course, for a convex problem, you only need the Lagrangian dual in order to satisfy global optimality. So in other words, the gap between the primal objective and the dual objective give you an evaluation of how far the primal problem is from optimality, right? Okay, so if the duality gap is 0, then you have a certificate that X is a primal optimal. And from an algorithmic viewpoint, we are not going to get strict global optimum. As long as the primal and dual is less than a tolerance, let's say you can pick an epsilon number, then you can terminate. Okay. Any questions here? So here we are going to talk about the last part of this lecture, which is called the Courage-Quinn-Tucker conditions. I'm sure you have heard about that in the literature. So this is the optimality condition for, at least for convex problem. This gives you a sufficient and necessary condition. Okay, so if you talk to some of the older people, they may only know this as the Quinn-Tucker condition. Okay, so the reason is that Quinn-Tucker published their paper, I think in the 1940s, And later on, people find out someone named Karash, who should be working for the Soviet Union, but he didn't publish the paper in English, right? But Karash already discovered it probably almost 20 years before Kuhn and Tucker discovered this. And actually, this part of this condition is part of Karash's master thesis. So that will give you a sense what you can achieve in a master's thesis. Okay, yeah. So let's talk about this condition here, right? So the condition has 4 parts. The last 2 parts probably are the easiest to remember, right? It says when the solution has to be optimal, you need to satisfy the primal feasibility and dual feasibility constraint. This is almost very naive. It is given, right? Then it has to satisfy the complementary slackness. This is a condition we talked about in linear programming already, right? So it says for each of the inequality constraint, then the Lagrangian multiplier multiply this inequality constraint has to be equal to 0, right? In other words, either ui has to be 0 or the function hi has to be 0, right? Or maybe both of them are 0 sometimes. Okay. And the last part is what we haven't seen before, which is called the stationarity constraint. So it says if you take the gradient over x on the Lagrangian, then the gradient is 0. Okay, how to interpret that? It is almost like since the dual is, when you derive the dual, it's minimizing over x, minimizing over this Lagrangian function, right? And we know that at least for convex problem, or even for any optimization problem, in order for x to be a local minimum, then the gradient is equal to 0, right? That's why it's called a stationary constraint. If the gradient is not 0, then you kind of show that this is not even a local minimum, right? Okay, so now we are going to prove those necessary and sufficient conditions. Okay. So first of all, we are going to show the necessity of the KKT condition. So it says if the x star and the Lagrangian multiplier are primal and dual solutions with 0 duality gap. In other words, when we say there's 0 duality gap, meaning that they are optimal, right? Yeah. Since the dual is always a lower bound of the primal. If they have 0 duality gap, then that means they are primal and dual optimal. Then it says if those are primal and dual optimal, they must satisfy the KKT conditions. So let's show why this is true. First of all, by 0 duality gap, it already says fx star equals to g u star v star, right? This is just the claim of the condition. That's a definition of 0 duality gap, right? And then let's just write down the definition of g u star v star, right? So remember the g u star v star is a minimum over the Lagrangian. So we are minimizing over x, fx plus I from 1 to m, ui star right? So this equation is nothing but the definition of the dual function, right? Okay, so with that, I will argue that this is less than equal to, since we are minimizing, take the minimum of x, right? This must be less than equal to when you plug in x star, right? X star is just a primal optimal solution. So this must be less than equal to fx star plus f from 1 to m. Right. So this inequality comes from, in this equation, I'm taking the minimum over x, but x star is just an arbitrary x, right? So that's why this inequality holds true. Okay. So now I'm going to argue that it is also less than or equal to fx star. Why it is the case? Because we claim that x star is primal optimal, right? If it's primal optimal, fx star must be, x star must be feasible. So when x star is feasible, then ui and the u and v are also dual feasible. Then when x star is feasible, then this is less than or equal to 0, the ui are greater than or equal to 0, and then the lj x star are equal to 0, right? So we just treat primal and dual feasibility as given, since the claim already says x star, u star, v star are the primal and dual solutions. If they are they have zero duality gap, they must be primal and dual feasible. And then that's just, we can treat those as given. Okay, so now that's all the inequalities I want to write down. What do we observe from this, let's say, a chain of inequalities? So maybe ask this question, are those inequality constraints always equality? It is, right? Because you have fx star on this side and fx star on the other side, right? Fx star must be equal to fx star, right? So in other words, these two inequalities are actually equalities, right? Since you have fx star on both sides. Okay. So now let's look at from the second line to the third line, right? We already know that the second line equals to the third line, right? So in other words, x star is a minimizer of this optimization problem, right? For the second line to be equal to the third line, x star must be a minimizer of this optimization problem. Then what does that tell you, right? So if x star minimizes a continuous optimization problem, we know the gradient of x star must be equal to 0, right? So the first, maybe let's write it down in different color. So this blue inequality actually means that x star minimizes the Lagrangian function at u star and v star, right? Then which is equivalent to the gradient of the Lagrangian function over x is 0, right? So this already gives you one of the conditions here, which is the stationary condition, right? And we already showed that, of course, primal and dual feasibility are almost given, right? If you argue they have a zero duality gap, then they have to be primal and dual feasible. So now from this purple equation, what we can get? So from this, we can get each of these terms must be 0, right? If they are not 0, they will always be a negative term, right? Their signs are all restricted. Okay, so this purple equality gives us complementary slackness must be 0 for all I 1 to m. So now we are done with the necessity of the proof. Okay. And then if you walk through the proof, you quickly realize that we didn't use anything related to convexity, right? Even if when we are taking the gradient, even for a non-convex problem, in order for x to be the minimizer, the gradient also has to be 0. Okay, so this is a typed notes of the proof. Yeah, and a comment here is that we did not use anything related to convexity, right? So that basically says even if you have a non-convex problem with 0 duality gap, they still have to satisfy KKT conditions, okay? So that's why some of the non-convex solver are also based on KKT conditions. Yeah, I want to talk about this real quick because if you are in this domain, when you read the literature, a lot of papers will talk about constraint quantification. It may confuse you a little bit. So I want to talk about this real quick. Recall that we said when we have Slater's condition and the problem is convex, we have a 0 duality gap. That's why the KKT condition have to be satisfied if you have Slater's condition. But there are other conditions where you have to, once those conditions are satisfied, then the optimal solution will also satisfy KKT condition. Those conditions, you can find it on Wikipedia. In some of the papers, you may encounter those conditions. The point of having this slide is for you not to be too nervous about those conditions. It is nothing but some other condition similar to the Slater's condition. Okay. So then we are going to show the sufficiency of the KKT condition. So the sufficiency says when the problem is convex, then when X star, U star, V star satisfy the KKT conditions, then they are the primal dual solutions. Okay, of course, you need convexity here for it to be, in order to prove the sufficient condition, okay, because for non-convex problem, solving the KKT condition are only necessary, they are not sufficient, right? Yeah. So now a proof is quite simple. If there exists a primal dual that satisfy the KKT conditions, basically you can show that you have a strong duality where the first equality holds from stationary because when the problem is convex, as long as the gradient is 0, then you get the global minimizer, right? And the second comes from complementary slackness, which is this term goes to 0. Okay. Therefore, the duality gap is 0. Just to summarize, if we have a convex problem with Slater's condition, then you can show that the KKT conditions are both necessary and sufficient. Right? This is just a restriction to convex problem. Then you can argue that KKT conditions are necessary and sufficient. When you have non-convex problem, then KKT conditions are not sufficient. Right? Whether it's necessary or not will depend on whether you have constraint quantification or not. Okay. So here's an example if you want to derive the KKT condition for this very naive problem where we have quadratic constraints, quadratic objective and only linear equality constraints. We can use this as an exercise. For example, when we want to write the KKT condition of this problem, we need to have first of all primal and dual feasibility, right? So the primal feasibility is nothing but AX equals to B. Right. And here we do not have any dual feasibility constraint because this is an equality, right? Then the dual variables are unrestricted. And complementary can also be removed because we only have equality constraint. Of course, when you only have equality constraints, complementary slackness is always satisfied. Then the only thing we are missing is the stationarity constraint. Right? So if you do the Lagrangian function, let's call this maybe multiplier to be u. You take the Lagrangian function over x u. That will be x transpose qx plus c transpose x, then plus u transpose b minus ax, right? And then you take the gradient of the Lagrangian. This will be qx plus c plus minus a transpose equals to 0, right? Okay, so now we are done with the KKT condition. And you can show that the KKT conditions of this problem can be written down in this very nice matrix form. Indeed, when this is actually a square system. You have the same number of variables and constraints. In order to get the optimal solution for this problem, you only need to solve a linear system. Okay. For other more complicated problems, the KKT conditions are less trivial. Then you need an algorithm to solve the KKT system. That's what we are going to talk about in the next lecture. Okay, any final questions?